Good morning to all. So in this session, we are going to see this topic, formulation and properties of S parameters. So the scattering or S matrix representation of multiport network. So the scattering or S matrix is used to design and analyze RF and microwave circuits. So in microwave junction, there is an intersection of two or more components. So the output port, along with the addition, there may be reflection from the junction or other ports. So totally many combinations are represented by this S matrix. So generally in high frequencies and low frequency, for high frequency, S matrix and transmission parameters are used to represent high frequencies. So in syllabus only this S matrix is given. And for low frequencies, different methods like Z, Y, A, B, C, D and H parameters are used. So this yes, Z is also called open circuit parameters and Y is also called short circuit parameters. And these are used to design for low frequencies. So this S matrix parameters measured with a network analyzer. So this network analyzer is used to measure both magnitude and phase of the S parameters. Also, it is used to calculate other parameters like insertion loss and return loss. So let us see what are the applications of S parameters. So it is used for filter design, amplifier design, antenna designs. They also used for network analyzing and matching. So the advantage of S parameter, so this S parameter is it will provide a complete characteristics of a network. And then short or open circuit test can measure or can make the transistors unstable so that it is not suitable for high frequency. So the matched loops are used for termination. It absorbs all energies, that is the incident energies, possibility of serious reflection back to device. So transistor does not pass by. So in the scattering array S matrix, so we can see this input power at the nth port is given as Pin is equal to 1 by 2 modulus of AN square, or reflected power at the nth port is given by PR equal to 1 by 2 modulus of BN square. If you are considering a two-port network, we can express the normalized waves in terms of the normalized voltage. So this A1 and A2 can be written by V1 minus by the reflection coefficients of Z naught. Similarly, we can write for A2, and B1 is the normalized reflected wave. So A is the incident wave and B is the reflected wave, which corresponds to port 1 and port 2. So this is the final equation for that A1, A2, B1 and B2. So the total voltage wave is the sum of the incident wave and the reflected wave. So incident wave is V plus and reflected wave is V minus. So we can write V1 equal to V1 plus V1 minus. Similarly, V2 equal to V2 plus V2 minus. And in this slide, so the total power can be written as P of I is equal to Pi minus PR. So I is the input power, R is the reflected power. So therefore it can be written as 1 by 2 modulus of A square incident power minus modulus of B2 reflected power. So if we are considering a two-port network, so which is B1 can be written as S11A1 plus S12A2, and B2 can be written as S21 of A1 plus S22 of A2. Since we are using a two-port network, it includes a square matrix of 2 cross 2 matrix. So we are getting this S11, S12, S21 and S22. So this S11 is also called input reflection coefficient, and S12 is called reverse transmission coefficient, and S21 is called forward transmission coefficient, and S22 is called output reflection coefficient. So S of 11 can be written as B1 by A1. So generally for S parameters, this S11, so this last term represents the input port and this represents the output port. For example, in S12, so the input is fed in port 2 and output can be taken from the port 1. So S of 11 can be written as B1 by A1, where A2 is equal to 0. So which means the reflection coefficient, the symbol at port 1, when port 2 in terminated with a matched load, which means A2 is equal to 0. So the symbol represents in S of 2 2 the reflection coefficient at port 2 when port 1 is terminated. So in the same way S of 1 2 is the attenuation of wave traveling from port 2 to port 1 when A1 is equal to 0. Similarly, S of 2 1 can be written as B of 2 by A1 when A2 is equal to 0. Output port by input port when A2 is equal to 0. Okay. So in general, by combining all this, we can write as B1, B2 up to B of n can be written as S11, S12 up to S of 1n. Similarly, in the column wise can be written as S11, S21 up to S of n1 into A1 to AN. Okay, then there are various laws which can be analyzed with this S parameters. So the insertion laws, transmission laws or attenuation laws, and reflection laws and return laws. So these laws can be identified with this parameters, S parameters. So insertion laws formula is a 10 log of PA by P naught. So input power by output power. So transmission loss is 10 log of PA minus PR by P naught, where PR is the reflected power and the reflection loss can be written as 10 log of PA by PA minus PR. That is input power by input power minus reflected power. And return loss can be written in terms of decibel is 20 log of 1 by modulus of S11. And these are the various properties of S parameters. So for S parameter, the first property is the diagonal elements are a 0. If you are using 3 cross 3 matrix, so the diagonal element of the 3 cross 3 matrix is 0 if the network is a perfectly matched. Okay, so if it is a perfectly matched, there is no reflection from any port. So therefore, under perfect match condition, the diagonal elements are 0. So the next property is symmetry of S for a reciprocal network. So which means a reciprocal device has the same transmission characteristics in either direction of a pair of ports and is characterized by a symmetric scattering matrix, which means S of ij is equal to S of j1 if I is not equal to j, which results in the transpose of S matrix. So that if you are taking the transpose of S matrix, which is equal to S, and this is the proof where the transpose of S matrix is equal to S for a symmetrical junction. And the last property is the unitary properties. So just a minute. So in this unitary matrix, so we can see a lot of equations. So for it, just a minute. So for unitary matrix, the summation of n is equal to 1 to n, S of ni into S of ni conjugate is equal to 1. So therefore, for a lossless junction, so in a matrix and notation, so this relationship can be expressed as the complex conjugate of S into S is equal to U, or the conjugate of S is equal to the S parameter matrix, the inverse. So here U is identity matrix or unit matrix. A matrix S for lossless network which satisfies the above three conditions is called unitary matrix. So this is the last properties, the phase shifter properties. So if the reference plane, if you are considering a two-port network, if the reference plane 1 and 2 are shifted outward to 1 dash and 2 dash by electrical phase shift of phi 1 and phi 2 respectively, then we are getting this 4 new variables. Then S matrix can be written as S of dash is equal to the new S matrix is S dash, which can be given as E of minus J phi 1 0 0 e power minus J of phi 2. So finally we can multiply this with this S matrix. So this property is valid for any number of ports and is called phase shift property, which is applicable to a shift of some reference planes. So these are the properties of S parameters. So thank you.